Good morning, people. If you guys would be so kind to type in the chat if you guys have any questions at all, I'm here for you. Mainly the free response or either multiple choice. Hi, guys. How are you today? I'm good. Just been fighting with YouTube. They keep on censoring me for copyright infringement, and I'm not exactly sure why. So my streams have not been lasting more than 4 minutes. So we're gonna try. Krishi, that's a great question. I do not have all the answers at this point in time. I'm actually in a conversation, an email thread with all the other AP science teachers, and we're trying to figure it out. So I know this morning I posted that you guys will have a test on Friday. I think I'm going to hold that off to at least. Hey, hold on, doggy. Hey. Okay. We're going to hold off your test till at least Monday once all the other AP science teachers get all on the same page. Assuming, like it has been, you're going to get multiple choice and a free response question. Exactly the details, I don't know, but it looks like now that I'm talking to the other AP teachers, you guys will do something on Monday. And by then, we'll have all the details about how you guys will take the test, how you're going to submit it, and we'll go from there. Hello. See, Akrishi, when we're done with the stream, I'll type something up on Google Classroom as a summary of what the test will look like. But once again, it won't be Friday anymore. It will be Monday because all of us AP questions are, trying to AP teachers are trying to figure it out. Let me just look at a calendar. Karan, you want to go back to, or Karan, you want to go back to school on a Saturday? Hi. So, Karan, is that what you want to go back to the back to school on a Saturday, the 21st? Actually, no, Karan. The governor announced, what was it, a few days ago that he wants public schools closed at least 2 weeks. So technically, that's today. Today was the first day of that closure, so we're talking at least April 1st. The thing is, spring break is the week after that. So if we go back the minimum, that will be April 1st, but then we'll have a week off for spring break. So, or a week until spring break. But yeah, as of now, it's a minimum of 2 weeks for all public schools. So at least April. And we'll go from there. Mm-hmm. Mm-hmm. It's my job. Hey, did you guys hear the good news that you can get Chromebooks now? Did anyone go to get one this morning? Okay. Okay, so if you guys are just joining in, just a quick update. I originally told you you guys were going to have a test on Friday. All of the AP Science teachers are currently in discussion about how to give you guys tests. So we will be pushing off the test to at least Monday, because we need to figure out logistics of things. So the test we had scheduled for Friday is getting pushed off till at least Monday. You guys are still responsible for doing the AP questions online. And what it looks like, only one of you have actually done the free response questions. Only one of you out of 17 or 16. And for the multiple choice, it looks like half of you guys did part B and half of you guys did part A. So I want to help you guys, especially those of you folks who actually practiced the problems and did the problems. I want to help you guys out a little bit. If you did not do those problems, you guys got to start doing those because you'll be responsible for them. And I can give you guys a grade, not necessarily for correctness, because I know we're trying to learn this stuff, but just for completion. So if you guys are struggling, please make sure you're submitting something, and then we can use these sessions to kind of catch up and help you guys out when we need to. So, do you guys have any questions or at all at this point in time? Krishi, I would love to go over a free response. There were two of them posted. Which one do you want to go over? The first one or the second one? Which problem do you want to go over? The first one or the second one? Okay. So before I go over the answers, do you by chance have it pulled up, or do you know what the problem is in detail? Before I start talking about the answer, did you actually look at it? Krishi and everyone else, did you guys actually look at the problem, or you just want me to go over it? Okay, just make sure. Okay, cool. Um, so for the first part, the tuning forks. Um, okay, a student has two tuning forks, X and Y. Okay. So this. Okay. Marker attacking me. Hey, pagers. Hey. All right. So this problem is all based upon. Yeah, I know, guys. We're improvising right now, so I know it can be difficult to type some things up. If it's easier, you guys can always take a picture and upload it as a PDF or a picture of some kind if that's easier for you guys. Um, Anyhow, though, for this first part, it's all based upon this equation V equals F lambda. In this case, once again, they're asking about the frequency, the speed. The only tricky part is that it's asking about the length of the tubing, not the wavelength. But if you recall, if this is L, and if this is an open tube, that means the wave looks like this. All right. There's two antinode regions and one node region. This is one complete wave. Okay. So a wavelength is two antinodes. So in this case, a wavelength would be 2 would be 2L. Okay. So in comparison to the question that you have, sorry, bear with me. Just making. So in terms of this comparison, your wavelength is going to be 2 of those lengths, and the frequency, the speed is frequency times wavelength. So if you put it all together, and they're actually asking for deriving an expression for Lx. So that would mean V equals F2L. And then, so in this case, the Lx is the frequency of the air. How do they word it? Fx2. something like that. I may have the terminology with the variables a little confused or backwards, but that should be what you're looking for. An expression for L with the frequency and the wavelength, like that. Okay. Krishi, am I good to go on? Since you seem the only person with a question, am I okay, or do I need to go over that part again? Okay. Let's see. What does it say? For that's A. And in the tube shown in figure 2, sketch represents here. Okay. Yep, part 2. Sorry, I was just looking up ahead, make sure I understand how to do the problems for you guys. So for part 2, they're asking about 2 different ideas. The first picture that we drew before in the previous problem, once again, if this is L or this is L, the most basic wave that you can draw looks like this. Okay, remember this is a half an antinode. That's an antinode. This is a node. Okay, so that's what the basic wave looks like. And once again, in real life, this is actually air pressure going back and forth. It's not a physical wave going up and down. So this picture is used as a visualization for the particles moving. So in this area, the particles are moving the most. This area, the particles are not moving. This area, particles move the most. So this would be a picture of the displacement. So if you ask to draw a picture of what the displacement looks like, it will look like something like this. Once again, this is the most basic one that we can draw in an open-ended tube on both sides. This represents the displacement, how much the air molecules actually move. Okay. But what actually happens in here because of pressure, once again, you could think of it as, once again, if everything is moving back and forth, back and forth, back and forth, when you think about the pressure point of view of it, in the ends, there essentially is no pressure. And the reason why I say that there's no pressure is because the waves are moving over there, so it's not bearing down on the actual tube. The pressure is the biggest at the node region. That's where the air is standing still, so that's where it's going to have all the pressure. This area will have relatively little pressure, if no pressure, because this is where the particles are all moving. It's not bearing down on each other. Here is where you would get the pressure. Here is where you wouldn't. So depending on how you want to do it, either pressure-based or displacement-based, you guys probably think displacement is probably easier to draw or easier to understand. But once again, pressure-wise, these areas have all the movement, so the pressure will be very low. This area is where the air is standing still, so it would have higher pressure. So something like that. Or actually, I should say, it could be like that too, just the opposite. Is that okay, Krishi? Okay. So then for B. Okay. So for the second question, B, well, I guess is it 2B? Am I reading that right? The tube of length fence is not. So the important thing about the next question is that um, for x and y, this is fx, this is 1/3 fx. All right, so for the next part, the tuning fork x has a certain frequency. Tuning fork y is 1/3 that frequency. In this case, they're both going to be in an open tube. Once again, this is kind of what it looks like, the open tube idea. All right, here's the key part of this. The key part of that is that the velocity of the air, the wave going in the air, is going to be constant. That's the key part about this. So if you think about the equation like we did before, V equals F lambda, and then if we eventually get lambda equals, oh, I forgot already. What was the answer to the first part? V over 2 Fx. Remember, we got this equation from the first part. The L equals the velocity in air over 2 times the frequency x. So in this case, obviously, if this guy gets smaller, all right, this guy is going to have to get longer. Okay. So once again, the actual answer is longer. You could think about it mathematically speaking. If the frequency gets smaller, the L has to get longer because of the inverse relationship. Keep in mind, you could also do something like if the V is going to be the same between the two trials and the frequency is going to be smaller, then the wavelength is going to be bigger, which makes the length of the tube bigger. So there's a few different ways that you can talk about it, but it's actually all based upon the two things: the equation you got before, which has that relationship, and the fact that the V in air, the velocity of the air, is constant between the two. So you can give me a yep if you're good on that one. Okay. Yes, it is longer. Once again, if this guy gets smaller, this guy, where is it? This guy gets bigger. Yes. That's correct. Okay. Creature, are we good? Okay. So for the next question, now we're finally comparing the two. And once again, we can actually use this equation that we have. We can kind of base it off of there because of the work we've done to this point. Because they want to know about the length, right? Okay, yeah, they want to know about the length of the tube. So remember, we have this starting one in terms of f of x, but we do know that f of x and y is a third of the frequency. So I can actually break this up into two parts. V 2fx will equal, because we want the lengths to be equal to each other, v 2 1/3 fx. Once again, in this case, they're asking about the length to be the same, so we could set these two guys equal to each other. Once again, the v is going to be consistent in both situations, so we can actually get rid of it. So 1 over 2 1/3 fx Okay, so I'm getting there. In this case, once again, the v is the same, so we don't have to worry about that. There's also another variable that is the same that we could essentially cross out. So in this case here, the fx is actually both the same. So also the 2's are the same. So really, in this case here, the only difference is to get the L, we're dividing by 1/3. So in this case, the length would be 3 of the original one because we're doing 1 divided by 1/3. And they call this the length of the short. Length of the short. Okay, so once again, for this one, we know that the L, we want the L's to be the same in this situation. So I'm setting these two guys equal to each other. Once again, if this frequency is going to get smaller, that means this guy is going to get bigger. So 1 divided by 1/3, we get 3. If you want me to rework it another way, I can. If we want to start from the beginning with v equals f lambda, I could also do it like that for you as well. And once again, you could just tell me if we're good to go. Okay. We're getting there, you know. All right, part 3. Oh, well, part 3's, yeah, it does. Once again, we figured out that the frequency was 1/3. We figured out, I actually don't even remember what the question was. Here we figured out, though, that the length of the tube is going to be 3 times longer. And our question in part 1, do I write the 1, 2? Yes, that makes sense. Once again, in this case here, we needed a longer tube to get this one working. So in this case, if we needed a longer tube to get this working, and this is a third, if we had a tube 3 times longer, we can get both of them working. And that's what this equation is all about. So yes, it does make sense. We expected a bigger number, and we actually got it's going to be 3 times bigger in this case. So yes, I would agree that we did the right thing. That may have been very wordy just now. But yes, bottom line, in part 1, we expected the answer to be longer, and our answer for the combining them is longer as well. So that brings us to, boy, they really mess up the wording of these numbers with like part 2i and 1a. It's not very nice. All right. So it's a pretty picture one. Okay. Once again, I think it's easier if we just talk about displacement. So we're just going to go with that. Okay. So in this case, we have a tube. So once again, we have a basic tube. Okay. I'm going to call this one X, and this will be Y, like so, just for us to make a reference here a little bit. Okay. Now notice they're asking about the LS, which is the longer tube. Part C. Yes, that's what I'm on, part C. So the tube that they're asking us to draw right now is the longer tube. Remember, this is the tube for this one to work the first time. So that wave is going to look something like this. Once again, the most basic wave that we can draw for an open tube is 2 antinodes and 1 node, like there. Now, once again, this is the most basic one that we've done. And keep in mind, there's a 3-to-1 relationship here. So if this has a frequency like this one should have 3 waves in this same span. So that's going to be 3 antinode regions. So that's going to look like something like this. So there's a node, a node, a node, antinodes, antinode, antinode, antinode. So here you have 1 complete antinode. Here you have 3 complete antinodes. Keep in mind the N ones are cut in half, but you still have complete ones there. So that is what this will look like if you look at displacement. I'll even write that down again. So these are displacement ones. So once again, the Y one is going to be the most basic, and the X one, we can squeeze more of them in there because it's a longer tube. Okay. Cool. Did we just do a problem together? Yeah, I think we just finished that problem. Or no. What am I missing? There's more to this, right? What am I missing? Oh, I'm missing D. Where's D? Ah, there it is. All right, so part D. Oh, beats. So, did you see the video that I made the other day about beats and how they basically work? Did you catch that on the replay, or were you live there? Okay, so Krishi, my recommendation is when this stream is done, you go on my page or to Google Classroom and find the lecture on beats. Beats basically occur. We've been talking in class about the amplitudes getting bigger or smaller. Once again, when they get bigger, it's constructive interference, and when they cancel out, it's destructive interference. So we've been focusing our attention on amplitudes. The same thing can happen with the frequencies and the wavelengths. So as a quick summary, this is not the scale. If I have a wave like this, once again, it's not the scale, and I have another wave like that, a big one, okay, these guys are going to interfere. But since the areas don't match up perfectly, we're going to get a unique pattern. For example, hello, up here is the crest of this wave, and it really coincides with the crest of that wave, okay? So right smack in the middle here, if we put this wave together, we're going to get a big part, a big hump. Here, this is a trough, all right? That trough is almost going to that crest. So this area is going to be like nothing. Same thing here. This area is doing pretty well, so that will be kind of big. This area and this area, that's kind of small, so this will be kind of here. And basically what happens is there's a good area, there's a good area, that's big. You're going to see a pattern come up. And the waves, I know it's not the scale, but this is actually what a beat is. It's a difference in the frequencies. Okay? So practicality purposes, if this wave had a frequency of 10 hertz, and let's just say this one had a frequency of 8 hertz. This one's 10, this one's 8. The frequency of the beat when they intertwine would be 2 hertz. It's because of the difference. So that means every 2 hertz, the waves coincide again or cancel out again, depending on your point of view. Now, if you bear with me a second, I have to go stop the dog from eating the wall. So bear with me a second. Come on. All right. So with that being said, for this question, you want me to throw the ball? I'm going to throw the ball. Oh, good catch. All right. For the nature of this question, they tell you, what is it? They tell you the period of one wave and the period of another wave. Okay, so by the record, this is actually really easy. Explain how the two waves can give rise to the beat phenomena. It's basically what I just showed you. The idea that since the frequencies are different, um, the crest of one wave will hit the crest of another wave, not at the same spot. So there are areas where that crest will destroy the other wave, and there are areas where that crest will constructively interfere with the wave. And that's why we get different beat patterns. Calculate the beat frequency of the two waves. There's two ways that you can do that. Method one, frequency is 1 over the period. So the frequency of A would be 1 over 0.01, and the frequency of B would be 1 over 0097, like that. Page. Let me just get a calculator because that part of the answer is not given to me. One divided by 0.01. That should be 100. And 1 divided by 20. That's 103. 103. We're just going to call it 103. Okay. So the difference here between this and this, the frequency of the beat would be 3 hertz. Okay. So that's one method of figuring this out. Okay. The other way that you can figure this out, if you know the time A is 0.01 and the time for B is 0.0097, you can subtract those guys. So let me just get my calculator again. 0.01 minus 0.0097. Sorry, I'm looking for a function here. No, what did I do? No, this is the way to do it. Forget what I was about to do. You're going to have to do this guy. Okay? So now I think we're good. I think we're done with that question. So good job, everyone, for the success. Yay. Okay. It's my job. Okay. For you peeps who are just coming in, just in case you didn't hear, all of the AP Science teachers are right now in a group email trying to figure things out. You guys had a test plan for Friday. I am going to be pushing that back till Monday, at least at this point in time, because we have to figure out the logistics of how to give you guys a test. But it will be on waves. It'll be multiple choice and free response. The only question we're trying to figure out right now is how you guys give us the answers without us without you guys cheating. That's basically what it's coming down to. So your test will be on Monday. I will probably do another stream for you guys on Friday, not 2 hours, but like another one because hopefully you guys are practicing before that a little bit. But I'm here for you guys for the next hour or so. So if you guys have any more questions, multiple choice or free response, please go back in this video. We did the first free response problem. And yeah, so what else you guys got for me? Sure. Let me just pull it up. Guys, I'm going to mute you for 2 seconds, okay? All right. Can you guys hear me again? I think you guys can, right? You can hear me again? Yes, you guys are good? Yeah, okay, good. Let's see. Oh, this one's a little different. Oh, that's a weird picture, huh? I'm just reading it because, you know. Okay. So the tricky part about this question is exactly where the wave is going to be colliding. So I'm going to draw a little grid. And Okay. This is my... Okay. So I've got two little grids here. This is what I'm going to have before they collide. And this one I'm going to have the moment they do collide. For argument purposes, I actually want to add another row. Like so. All right, the key about this, and once again, it's really hard to understand. That's two. Oop. That's two. Okay. So the key part is, this is what the wave actually looks like. And the key part is that this is the actual wall. Okay? And here is the center. So what actually happens, and you guys have done this in class, when you have a fixed point over here, this wave is going to turn upside down. Okay? So what should happen if this entire thing turned upside down is that this piece will be 3. Oop, I'm sorry. Other way around. Is that this piece will be 3, or 2 boxes like this, and then that piece goes upside down like that. So that's what would happen if you guys can see the difference between the purple and the blue. The purple is what it looks like coming in. The blue, it's gonna look like what it comes bounced. But they say in the problem that only the first half of the wave has bounced on this point. Paige, stop. No. Hey. Only the first part of the wave actually bounced at this point. So you're going to have both of these conditions. Okay? I'm sorry, both of these conditions. Because the purple one is still moving, but the teal one already bounced. So it's going to look like these two added together, but going the other way. Paige. Sorry, the dog's destroying her bed. So 1, 2. Okay. So it is going to look like this is the wall. So it's going to look like this. Okay. Once again, you have the triangle portion, which is going towards the wall, and the square portion, which at this point has flipped over and is going back away from the. I keep on getting confused with the camera here. This triangle portion is going towards the wall. The square portion was going back that way. So the moment they actually meet, they're going to impose upon each other, and you're going to get a trapezoid or pentagon shape in it, because that's where the two actually meet. Once again, half the wave has been hit already, so it's going to flip over, and they're going to constructively interfere with each other. So it's going to look like this. The amplitude total is going to be 4, and the shapes are going to be put together. Is that okay? Okay. For B, Oh, there's a lot of text here. A student labs. Okay. So for that second part, there's a lot of things going on. Okay. So let me see if I get this set up right. We have one guitar. That's L. The other group makes another one. Imagine these guys are at a scale. This is L, this is 2L. Okay? Here, I'll get rid of that guy. So imagine that that's the scale. That their fundamental frequencies are the same frequency. FF, and this is FF. So in this case, once again, on a standing string, that's what the waves will look like, and they operate at the same frequency. And clear coherent paragraph long may also contain equations to drawing state how both the resulting standing waves on the strings and the emitted sound waves are the same and or different between the two groups. All right, so the tricky part here, once again, what they're asking about specifically, the standing waves on the strings and the emitted sound waves are the same, okay, or different. In this case, they are going to be the same sound wave and the same standing wave. So these guys are going to be the same thing. If this was heard, you would hear the same thing. Now, here's the tricky part about this. Okay, let's start off with V equals F lambda again. Okay, once again, and when it comes to sound waves, we know the velocity of air is consistent. Okay, we know that that's consistent. So in terms of what we hear, the frequency is going to be the same. The wavelength is going to be the same because the velocity in air is going to be the same. We're going to hear the same thing regardless. Okay. Okay. Here's what we're also going to know. If you think about the equation V equals F lambda, and the idea that a wavelength is two antinodes, so in this case, the wavelength is 2L over N. We know this guy, okay? Obviously, if this guy has twice the length, the wavelength is going to be twice as big, okay? But now you're asking yourselves, how is that actually possible? What is actually going to go on here? And it's kind of hard to imagine, if you would. But this wavelength is of the string. The first comment air would be different. So imagine, if you would, that both of these strings produce sound waves. These sound waves have the same wavelength. These sound waves have the same wavelengths. These wavelengths are going to be different. The wavelength in the string is going to be different. So don't let that confuse you. If you use both of these equations together, it's going to tell you the wavelength can't be the same. It can be the same because this wavelength is in the actual string. This wavelength in this equation, because of air, is going to be the same. Now, if you recall, when we did this stuff, you had this guy to describe the velocity in the string, okay? The force of tension over the coefficient. So in this case here, in order for them to be the same frequencies and a different wavelength, the issue is going to be tension. The tension is going to be different in each of the scenarios. One string is going to be tighter than the other one so that they get the same frequency. Okay. So let's see. So once again, the issue is 2. So in this scenario, it's going to go twice as fast. I should actually say this. For this scenario, the wavelength will be 2 times bigger. Okay. If the wavelength is 2 times bigger, the speed is going to be 2 times bigger. And in this case, if the speed is 2 times bigger, the tension in it is also going to be bigger by the square root of 2. I believe it's the square root of 2 in this case. They don't actually have that as part of the answer. But this guy will be tighter. The FT here will be tighter. What else do they bring up in this response? Yeah, I think that covers everything about it. Okay. Is there any other questions or things that I didn't clarify about the second scenario? Once again, the frequencies can be the same. You're going to hear the same sound because the wave in the string is different than the wave in the air. So don't let that confuse you at all. These equations we get based upon the string. This equation we base upon the air. Page. Sorry. Page. Okay, cool. All right, what else you guys got? Okay. Okay, Archana, give me a second. I'll look those up for you. Okay. And you said part B, 8 and 9. All right. So 8 and I think 9 as well. I covered in my last stream, I think, but I'll go over those again. In this case, we have a tube. It's open at one end and closed on the other. Okay. Cool. Okay. Enjoy your lunch, Creasy. Don't forget to wash your hands. You know, you were typing and holding pencils and stuff. In this case, because the tube was closed at the end. Hi. Are you so excited? Okay. This part is closed. Sorry, my Mrs. Kesh just came home, so the dog's all excited. So if you guys hear her in the background, this region is going to be a node because of the closed end. This region is going to be an antinode because of the open end. So the most basic wave that you can make with an antinode on one side and a node on the other side, it's going to look something like this, like a cone. Okay. So now here's the thing to remember. A wavelength is two antinodes. Okay. In this case, we only have half of a wave. I'm sorry, half of an antinode. So we need four more pieces of it. So if this is L, we need four L's to equal one wavelength. That is why the answer is V over 4. Oh, I didn't actually read the question. Getting a little confused. So, hold on. V equals F lambda. All right. That's the idea for this one. V equals F lambda. Graph S as a function of 1 over L. And find that the slope of the graph is equal to 1 over 4. Okay, or V over 4. All right. So, that is how they get the 4 in the slope. F as 1 over L. So if we use this idea and plug it in here, we're going to have V equals 4F L, like so. Okay. 45 I want to show. If we move this over, F equals 4L over V. And if they graph 1 over L, this gets switched around to V over 4. I don't actually know if that actually helped you at all, or if you can get away with just this part here. But the idea about it is you definitely need an answer with 4 in there because of this idea that a wavelength is 2 antinodes, and in this case, 4L is going to be 1 wavelength. So A and C we can cross out right away. And then graphing F as a function of L would actually equal 4V in that case. It wouldn't be divided by 4. So I hope that helped you. I'm not sure if I actually did okay, Archana. But the answer should be D, if that's okay for 8. Okay, so your second question for 9, let me actually read this one. You have 2 tubes. A statement must be established. Okay, so in that scenario, it's based upon the same picture I just showed you. Tube X is open at both ends. So that's open, and this is for tube X. All right. If tube X is open at both ends, the most basic wave that we would get, this would be an antinode, this would be an antinode, and right smack in the middle would be a node. So this is the most basic wave that we would get in tube X. Keep in mind, all of this is going to be true. One wavelength is 2 complete antinodes. Okay, so this holds true for all waves in an open or closed tube or a string. One wavelength is going to be 2 antinodes. So in this case, if this is L, one wavelength will equal 2L. Okay, that's the nature of an open tube. For tube Y, there's a length L. This is open, this is closed. Where there's closed, it's going to be a node, and where it's open will be an antinode. So the most basic wave here is going to look like this. With this statement holding true, in this case here, one wavelength will actually equal 4L. That's, once again, because of the nature of how the wavelengths form in these tubes. So in this case, the student's approach is flawed because they're using a tube. Which one did they? The student uses tube Y. So they're not taking into account the fact that this is a node when they do the experiment. Changing the amplitude won't do anything. Um, Increasing the frequency would just change the wavelength. Same thing with C, it will just change the wavelength. You need to actually use the tubes. No matter what you do, you're never going to get two L's out of this guy compared to this guy. It's not going to happen. These pictures will always be different regardless of the frequency. So I hope that explains D. Once again, to Y, it's going to look like this. By definition, you need 4 of them, but open tubes are going to look like this. You only need 2 of them, and that's what they should be using. And this is why. Okay. Okay. Folks, I'm going to be on for another half an hour or so. If anyone else has any more questions, I'll be happy to go over them. Okay. You folks that are still watching, do you have any questions at all? Okay. Guys, this is the last call. Does anybody have any questions at all? Going once, going twice. Okay. All right. So for that question, Pratham, do you have it open right now to look at it? Okay. So A and B are definitely not the correct answers because the student is absolutely not correct. Um, the frequency is determined by the sound of the I'm sorry, the speed of the sound. In this case, it will be the air, which we know is consistent, and the wavelength. If the tubes are not consistent lengths, the wavelength will not be consistent. So A and B are completely wrong just because of the definition of how we find frequency and wavelength in a standing wave. The question becomes between C and D. The student is incorrect. Um, C says the student is incorrect because the length of each tube, along with the emitted frequency, determines if a standing wave is produced. Okay, once again, that's actually what I just summarized there because it's V equals F lambda. The V is going to be the same in both scenarios, but the wavelength is based upon 2L over in this case, the basic one. So once again, the length dictates the wavelength, and if the velocity is the same, the frequency will be different. The student is incorrect because the standing wave will be established both tubes. D would only be true if we knew that it was L and 2L. But since it is say that the L is longer, we don't necessarily know that it's exactly 2L or 4L or something like that. So we cannot assume that D will always be the correct answer. The correct answer has to be C. Mm-hmm. Okay. Guys, I'm just going to go to a little teacher's room. If you guys have any questions, just leave them in chat. And I'll be back in about 2 minutes, okay? Okay. All right, guys. Any more questions at all at this point in time? All right, guys. I think we're gonna call it then today. Um, Thursday I will not be on streaming, but Friday I'll give you guys an opportunity to, and I'll know Friday what the status will be for your test on Monday. Exactly how we're gonna do it. So once again, keep an eye out on Google Classroom. Try to do the multiple choice and the free response if you haven't done it already. Um, and once again, I'll be back on Friday for you guys if you have any questions. Okay. All right then. We'll see you guys Friday. Be safe. Don't forget to wash your hands, and we'll see you then. Bye bye.